Okay, thank you. So hello everyone. So my talk is going to be very much in the line of Lenka's. It's going to be an application of the replica formalism to deep neural networks. So I also planned an introduction that has a fair overlap with hers. So if the coffee break was long enough for you to forget, rejoice. Otherwise, bear with me for a couple of minutes. So deep neural networks are parametric models, and they are made of artificial neurons that are little units that are function of a weighted average of inputs. So they have two kinds of parameters, weights and biases. And they bear an activation function that is typically nonlinear, either hyperbolic tangent or rectified linear units. And deep neural networks are a combination of those little artificial neurons that are organized into successive layers from an input to an output. And the intermediate representations, we call them hidden. And I will denote them by the letter T in the rest of this talk. So we can gather all the parameters of such a model into weight matrices for each layers and biases vectors. And in this way, we can write very compactly the function that is defined by such a deep neural network. That is highly non-trivial. And actually, it has a great representative power. So there is the remarkable universal approximation theorem that Lenka also mentioned that states, so informally, that for any continuous function that you are interested in, there exists a two-layer neural network, so with a given number of hidden units m, and proper values of the weights and biases parameters, such that the function that you are interested in is well approximated by the simple neural network. So it's a very powerful result, but of course, it doesn't tell you how you can find those parameters. And what people do in practice is that they consider a much deeper models, so with much more hidden layers, that have a very large collection of parameters. Then they do some machine learning, so they consider training data sets, so to learn the rules they are interested in. They have examples of input and output pairs. Then they look at the errors that the network is making by comparing the true outputs with the outputs that are predicted by the network. So that, for example, can be just a squared distance. And then they are going to minimize this error. And as Lenka was saying, the basic idea behind all the optimization algorithm used in machine learning these days, in deep learning these days, is gradient descent. So this is an heuristic approach, but that is highly efficient. So now we can consider having automatic vision to the level of thinking of driving cars, etc. And there are intuitions into why it's working so well. One of them is that depth allows to learn some hierarchical and invariant representations of the data. So imagine the task where you want to classify images of cars according to their brand. Well, if you feed a deep neural network with such a training data set, and that you look at the end of the learning what the different layers have learned, you will see that the shallowest layers, they learn some simple features, such as detecting edges, whereas the middle layers, they are starting to learn some car parts, and the deepest layers are really having detectors of the different car brands. So this is an intuition, but if you are trying to more mathematically understand why deep neural networks are working, you encounter a lot of puzzles. So one of them is the optimization that we've already heard about. So of course, the error landscape is highly non-convex, and so we have a very poor understood of why gradient descent is yielding good results here. And another one is generalization, which was also introduced by Lenka. So we are really in this regime where we have somehow more parameters than points in the data set. And so we would expect that having so many degrees of freedom, we would have a fit that looks like this, where we are fitting all the noise in the training data. And that this would be a very poor model to predict on new points that were not seen during the training. Nevertheless, we actually observe that deep neural networks are having a very good fit of the data. And this is not well captured by the usual tools of statistical learning theory. So there is an alternative proposition that was made a few years ago, that is to look at a deep neural network through the prism of... Sorry?
In which sense you say it is not?
It's not well captured by statistical learning theory, because if you look at the bounds on the generalization errors that are predicted by statistical learning theory, they will be way too pessimistic compared to the practice. So they are not useful. And one reason is because they are very generic. They are valid for any data distribution. But if you want, I mean, the statistical learning theory would predict that I generalize very badly with a deep neural network, and this is not what we observe in practice. Okay? Okay, so one proposition is to look at information matrix. So more exactly, I mean, what we are going to be interested in, basic definitions. So we are going to look at entropies, okay, of distributions, and at mutual information. So for two variables, x and t, the mutual information can be defined as the KL divergence between their joint distribution and the product of their marginals. So it's a measure of how they depend on one another. It's zero if and only if they are independent, and otherwise it will be positive. So those kind of integrals are, of course, very hard to compute because they are very high dimensional. But here we will see that Replica can help. And the mapping to the disordered system is the following. So we are going to consider the case where we are interested in a random variable t that is coming from an input variable x. And in this case, the distribution of the layer will include a marginalization over the inputs. And this is all that we need to recognize a partition function as a statistical physicist. Then, if we want to compute the entropy density, it's actually going to be an average free energy density. And so the expectation of the log partition. Then, of course, we can apply the replica trick. And in some cases, find an asymptotic value for the entropy that will be the minimum of replica symmetric potential. So here it's going to be replica symmetric because effectively we are taking an average of the log partition that is with the same disorder as the one so the same distribution on T for the average than for the computation of the partition. And so this is why we are alike in a planted system, and we have the Nishimori conditions, and things will remain replica symmetric. Okay, so in which cases can we proceed? So there was a result about single-layer neural networks already by Yoshiyuki Bashima and collaborators. That was for the case where we have a known distribution of the inputs that is factorized over its dimensions. And when orthogonally, weight matrices are orthogonally invariant, which means that when you compute their singular value decomposition, the basis matrices, or the orthogonal matrices U and V, they are independent samples from the R measure, that is the uniform measure over orthogonal matrices. So you need to have these statistics over the U and the V, and then your singular value matrix can be arbitrary. In this case, you have so a result of the replica computation that is given as the extremization of a potential that has 4 parameters. And okay, I'm not even defining everything that is in this formula, but something I want you to notice is that you have the prior of the inputs that is intervening in one term, and the stochastic activation of the single layer on another term. And those are mutual informations and entropies of scalar variables, so they are easy to compute. So now, what about multi-layer neural network? What we realized is that it could be derived recursively. So from this single layer result, so this is just a copy-paste from the last slide, I can here draw a heuristic derivation of the 2-layer result. So the idea is first to look at only the single-layer model T1 from T2, apply the results of Kabashima, and then here I actually cheated a bit because the distribution on T1 is not factorized, and therefore this mutual information is not trivial. Nevertheless, I can use the definition of the mutual information that can be written in terms of a difference of entropies. I will have one that is the entropy of a Gaussian auxiliary variable that is easy to compute, and another one that is the entropy of the first layer augmented with a Gaussian, and that I can actually compute by considering the result of the first layer. So by combining models, I can really go to multi-layer and recursively go deeper and deeper. And so this is the result. So again, if I know the input distribution and that it's factorized over its inputs, and if my weight matrices are orthogonally invariant, then I have, in the limits of infinite widths of all the layers, a formula for the entropy of the output that is given as replica, the extremum of replica potential. And this potential is additive over the layers, so I can go as deep as I want. I can just add terms to this potential. It depends on the weights through their spectrum. And it's a function of scalar, of entropies and mutual information of scalar variables that are easily evaluated. So ultimately, what we did is that we replaced the high-dimensional integral to compute the entropy by an extremization over 4 times the number of layer variables, and this can be done efficiently. So why do we trust this replica result? I'm not sure I should, maybe this crowd is not questioning so much the outcome of replicas, but we have a couple of reasons. So one is that the result that we get is consistent with multi-layer results, but for a smaller class of random weight matrices, which is matrices with IID entries. In this case, we also have a mathematical proof that for up to 2 layers, the result is rigorously exact. And we also have a consistency with other heuristics that are involving orthogonally invariant matrices. So a first application of this estimator, now that we have it, is to compare it with other strategies to estimate the entropy. And a very powerful strategy is to have a nonparametric approach, where all that is needed to construct an estimator of the entropy is a set of samples from the distribution we are interested in. So basically, the way it's done is to have a certain number of samples and look at the pairwise distance between the points. And there are different strategies, but this allows to estimate some entropy. So we considered the following experiment to make the comparison. We look at a small 2-layer network with Gaussian inputs and Gaussian weight matrices that have variances that are parameterized by a little sigma. And then we look at the entropy of the second layer as we vary the weight scaling. And we start with linear activation functions, so linear f's here, because in this case, there is an analytical formula for the entropy if we have Gaussian inputs. And so we can benchmark the estimators with the exact analytical result. So this is in black, and actually the replica in red is perfectly superimposed. And we can see that the 2 nonparametric estimators that we tested are capturing the right trend. As we are increasing the size of the weights, they are seeing how the entropy is varying. But they have a systematic bias. Now, if we go to cases where we will not have anymore any exact benchmark, we can still compare the replica methods with the nonparametric estimators. And we see that in this case, they don't really coincide. So for the ReLU, they are completely losing, the replica is having half of the slope of the nonparametric estimators, so they are completely missing out. And for the hard hyperbolic tangent, which is a piecewise linear approximation of an hyperbolic tangent, we see that they also have a systematic bias at low variances and then don't exactly capture the point where it starts to decrease. So here we see that the replica estimator needs a lot more information than the nonparametric estimators. It needs to know the distribution of inputs, all the activations, and so on. But in this case, it yields a very accurate estimation, whereas more generic methods are failing to be as good. So now Another application that motivated a bit us going in this direction was this idea that we should be looking, at the mutual information between layers during the learning of deep neural networks. So how they are going to depend on another. And this idea attracted a lot of attention from the community after the following experiment was published. So the idea was to look at a small classification task. So the output was plus or minus 1. They had a very small network, so there are no more neurons than the ones that are drawn on this picture in this experiment. And they had hyperbolic tangents with activations that were binned, so discretized, so as to have a way to compute the mutual information. And in this case, this is what they saw. So they saw on this plot where you have in the x-axis the mutual information between the input layer and the hidden layers. And on the y-axis, you have the mutual information between the hidden layers and the outputs that you are trying to predict. The different lines correspond to different hidden layers. And you have the time of learning that is color-coded. So black is the beginning of the learning, and yellow is the end of the learning. So on the y-axis, what we see is that for all the layers, the mutual information with the output is increasing, and this is reassuring because you are trying to learn how to predict the output, so you are happy to find that you are actually having a mutual information that is increasing. But something a bit less trivial is happening with the inputs, where you have first during the learning a phase where the mutual information is increasing, but at some point the trend is reversed and you have a compression phase. So this was interpreted as a forgetting phase, where the learning algorithm will somehow induce the hidden representations to forget about what's not necessary in the input data to predict the output. So the hidden layers would become more and more insensitive to the nuisance in the training data, in the input data, and really learn these invariant representations that we intuit are important to explain the successes of deep learning.
Sorry, could you just in that graph where we see this forgetting thing?
Yes. Okay, so this is the mutual information between the hidden layers and the input. And so the time of training is the color. So here, if I look at the deepest layer, it's first having a mutual information that is increasing, and then it's decreasing. And the same for the second to last layer, increasing, and then decreasing all the way to here. So it's really the fact that you have these turning points where the trend is going to go towards lower values of the x-axis. So this is the okay. Clear? Yeah.
So there is where you are eliminating the irrelevant aspects.
This is an interpretation of this picture. And it actually came with a debate because it's a pretty compelling picture, and it would offer some quantification of this intuition we have that we should be learning invariant representations. Nevertheless, it comes with a few issues, and one of them is that in deterministic neural networks, so when I don't have any noise between my input and my hidden layers, I'm not introducing any noise in the functions, then the mutual information is infinite. And the reason for that is because the conditional entropy here, the Shannon entropy on continuous variables can diverge to minus infinity, and in this case it does. So we need to regularize, and one strategy is to discretize value. This is what was used in the previously shown experiments. In this case, everything is well defined. Nevertheless, this is something that we need to do a posteriori of training, because we are training with gradient-based algorithms. So we cannot have discrete values before training. And actually, Andrew Sachs and collaborators showed that if you were deciding for discretization after training, so you could choose for different discretizations, you might get inconsistent results. So that was not really satisfactory. Some other strategy is to directly add noise to the continuous network. And this is pretty reasonable because it's actually commonly done in in the machine learning community to add some noise during the training And this is promoting the generalization of the network. So why not? But then we are left with, okay, how do we compute those very high-dimensional integrals? So I ran experiments with nonparametric methods. And actually, there are two high-dimensional problems. And those methods are not sensitive enough to be able to detect compressions. So instead, we can try to use the replica methods that we just introduced. And so our aim was to test the robustness of the compression phases in large networks, different nonlinearities, different data sets. So really try to see if it's a generic phenomenon. And okay, we had two constraints. The first one is that we have to know the factorized input distributions. And the second one is that we need weight matrices that are orthogonally invariant. Challenge accepted. So the first constraint is asking for synthetic data. Okay, if we have to know the distributions, then we are going to have to make up the data sets. And the strategy is to place ourselves in the teacher-student scenario. So it means that if I want to study the learning of this deep network, I need to feed it with input data that have IID components. So it means that if I live in 2 dimensions, I will pick a distribution, sample one of the axes, sample the second one, make a point, repeat the operation. So I have a data set of inputs. Now, if I want to do some supervised learning task, I will, for example, do classification. I decide for a boundary rule in my space, and then I get labels that are either +1 or -1. And so this will be my teacher rule and my students that I'm going to study the evolution of. And here I have my Markov chain that starts with the IID inputs on which I can apply the replica formula. Nevertheless, there is something a bit unsatisfactory about this strategy, which is that the data really has no structure at all. It's really noise, if you want. And we believe that structure in the data is crucial to understanding what's going on in deep learning and why it's working so well. So we imagined an alternative strategy that includes so-called generative models. So the idea is that we are going to start from a Z that is a hidden representation that has the property we are interested in, and transform it to get the input data set. And if you are, and this will give us a non-trivial distribution. And I mean, if you are a good machine learner practitioners and you use one of these training algorithms, you can transform plain white noise into pictures of cats. So this is something that I took from a paper. This is really generated in this manner. So this way, we would just need to add some teacher rule, and we could study the learning of the students on the dataset created from the teacher model, and still have the property of having a Markov chain that starts at a known IID distribution. Okay, so this is our first ingredient. The second one that we need is to have orthogonally invariant weight matrices. And this is how we imagine doing it. So after initializing the weight matrices for our gradient descent, so it's traditionally done by having Gaussian IID entries, we compute the singular value decomposition. And then we keep fixed the 2 basis matrices. So they were originally samples from the R merger, and they are going to remain so during the entire learning. And only update by the gradient descent the entries of the singular value matrix. So, of course, this has the cost of only learning n parameters, if you want, per layer, instead of n squared, but this is what we can do. So we have our 2 ingredients. We have a synthetic data set, and we have a weight preserving rule, preserving the orthogonal invariance of the weights. We also have the replica formula to compute the entropies. So now what does it do? What happens when we learn? So the first thing that we did was to look at linear networks, because again, this is the case where we have an exact analytical formula, so it's a sanity check if you want. And so we made up a data set and trained a linear deep network on this data set. And here I'm just giving you the plot that is showing that the learning is going well, because this is the time of training, and you can see that the loss is going to 0, and it's true for the training loss and the testing loss that is giving me the measure of generalization. But here I can see that the mutual information between the hidden layers and the inputs for all of them is only increasing during the entire learning. Okay, but what motivated me to do this experiment was actually to check the difference between the exact value of the mutual information and the one predicted by the replica entropy. And so I checked it for the 3 different layers as a function of the size of the problem, because the replica formula is an asymptotic statement, so I expect that it's only going to get better if I get larger. And this is exactly what we observe. So we look at the maximum error and the mean of the error over the entire training. And we have errors that are decreasing with the size of the problem, and that are anyway very small. So here you have a 10 to the minus 13, 10 to the minus 4 coefficient. So okay, we can learn those matrices, and the replica formula will remain exact, well, at least in linear network. And now we are going to trust that it's still the case in nonlinear network, which we are interested in, that are closer to actual deep learning problems. And so we run the first binary classification example. So we made up a little teacher network that was producing a data set and looked at a deep student with hard public tangent activations. And this is what we got. So here again, this is just showing you that the training is perfect. So at the end, I have a 0 loss, or I have a classification accuracy of 1. And here you get the different layers with the mutual informations with the inputs as the training time. So you see that you have compressions in all of them globally. And you have the little insets that are zooming on the first epochs of learning that are showing that sometimes you also have an initial increase. So this is consistent with the first experiment that I showed you. And then we replicated the experiment with reloos that are non-saturating. And we saw that we also have compressions in all the layers with some cases where it will also grow at the beginning. So with this experiment, we were able to observe that there can be also compressions in network with reloos, and this is something that was not observed before. But we also made second experiments where we kept the first setting with the hard hyperbolic tangent, but we varied the point of initialization of our gradient descent. So we varied just the width, the width of the Gaussian with which we are initializing the weights. So 1 over the number of neurons in the preceding layer is the common prescription, and so this is what we just observed in the previous slides. So compressions everywhere. But if we were to augment a bit this starting point or diminish it a bit, we can observe very different phenomenologies. In the inner layers, you may not have some compression at all. You may have something that is only increasing here also, and here something even more exotic is happening. So the takeaway from this little experiment is that good generalization, so that we get in all these different cases eventually at the end of learning, can happen without compressions. And this is also something that we had in the linear networks experiments, where we had good compressions, although good generalization, although we didn't have any compression. Okay, so with this I will conclude. And we saw that we could define a class of stochastic networks on which the replica formalism could be of some help to shed some light on some debates in the deep learning community. And in the experiments, we found that, there are some compressions with networks that have activations functions that are non-saturating. Nevertheless, they are not systematic, so it's not this beautiful, complete picture that we were hoping for. Things appear to be more complicated. And a perspective, nevertheless, of this approach is that people have tried to explicitly penalize the mutual informations during the learning to promote generalization. And it seems to be working quite well, and there are a few works in the literature about this now. And okay, there is. And with this, I thank you.
Thanks a lot. Okay. then I have one.
Okay.
I mean, so you were able to also to study the problem of regularization in this way? I mean, just for instance, the pruning of things on...
No, so when also... So one thing that we could be looking at, indeed, is repeat experiments and vary some methods of regularization and see if
Which
active...
methods of regularization you were looking at?
No, here, none. Because the thing is that gradient descent is already, I mean, if you don't regularize at all, you just do plain gradient descent without any constraint on it, it will already yield a result that is generalizing very well.
Okay.
And so this is what way we are studying, really the minimal model. But some direction of research could be, okay, now we look at different generalization methods and how does the compression phases are impacted or not by explicitly, actively regularizing the training. That I don't know.
No more questions? Then thank you again.